Welcome back, everyone. Here we're playing around with cylindrical and spherical coordinates, working through our group work. So to start off, we have a particular function that we are integrating over a couple of regions. So looking at our first region here, we're wanting to choose what coordinate system to set this up in. And here, because of the flat top and flat bottom, looks like cylindrical is definitely the winner in terms of cleanest. And so if we want to think about which variable to move first, either x, y, or z, here to me, I'm thinking about moving z first. So if we pick a particular x, y underneath this thing and move in the z direction, we're going to be starting at z equals 0, and then moving up, and then blink, coming out at the top at z equals, looks like the vertical stretch is 2. And that's going to be consistent wherever we start underneath this thing, always starting at z equals 0, coming out at z equals 2. And so we can start getting our integral set up. Moving z from 0 to 2. Now, to take care of the shadow, let's get a picture. Right? The question at this point is, well, what x, y's do we do this for? And so the shadow is going to be in the xy plane. And I guess it looks like a circular region, radius 3 is how far we are coming out. And so this is going to be our shadow underneath. And so we can describe this with polar, moving r, and let's see, settings, so theta, we're using thetas from 0 up to pi over 2. And for each one of those thetas, like this one, we're stretching r from r equals 0 out to the outer edge, which is going to be r equals 3. And so our polar dA here becomes r dr d theta, and our function here, x minus 2z. Z is one of our variables, but x is not, and so we'll swap that out. R cosine theta minus 2z, and there we go. We have our fully set up integral in terms of cylindrical coordinates. For our next one, definitely looks like spherical is going to be giving us something clean. We have a couple of spheres here, so definitely leading us that direction. All right. Well, to get a sense of what our limits are going to be, as per usual, let's look at a theta equals constant slice of this thing. Imagine one of those doorways just kind of swinging around. We pick a random theta equals constant door to slice this thing with. Let's graph our cross section. So we have a z-axis going up and r going out. And this thing is going to look like this. And so something like that. I guess this is connecting at 1 and 2. And so if we pick, say, a random phi to set and think about moving a row, so picking a phi, it's an angle off the z-axis. All right, so looking at it this way, let's move out. When do we want to start and stop row? Well, we want to start row right here at this inner sphere and stop row at the outer sphere, right? And that's going to be consistent no matter what angle we choose. And since these are boundaries of circles, spheres rather, we're always starting at row equals 1 and ending at row equals 2. And so we get our inside limits of integration. Right, and so here our dv is going to become our rho squared sine phi d rho dv d theta. Right, now our question is, well, what phis and thetas are we doing this for? Well, from our picture over here, our theta equals constant slice, we can see, well, we are using our phi angles from 0 down to pi over 2, right? Phi equals 0 points us up along the z-axis. Moving down to pi over 2 will get us pointing horizontally. So 0 to pi over 2 for phi. Theta, our boundaries, come from our 3D picture over here. And I think at this point it might be helpful to look at a top view of this thing. We look at a top view, so the z-axis is kind of staring at us, and x and y are looking like this. This thing kind of looks like, let's see, no. It's connected to the y-axis and then swings around, kind of like this. This is what it would look like from the top. And well, what angles are we using? All right, we want our angles to be increasing, and so we actually are going to start at pi over 2, and then keep moving up through pi, through 3 pi over 2, all the way up to 2 pi. So from pi over 2 all the way up to 2 pi would be our boundaries for theta. Those are the thetas that we're using. We've got to translate our function, which is x minus 2z, I believe. Let me just double check. Yes. All right, and so here we just need to use our translation equations. I don't have these memorized off the top of my head, but you probably don't either, so let's remember them together. All right, so we have the picture that we can draw. Here's our point, here's rho, here's phi, here's r, here's z. All right, this is our theta equals constant picture, yeah. And so, let's see. So z is this side, it's the adjacent side. So z is the going to be rho cosine phi, and x is r cosine. Oh, sorry, I said phi. I wrote theta. Going a little bit too fast. X from polar is r cosine theta, and r from our picture here. Oops. R is going to be rho sine phi, and so x is rho sine phi cosine theta. And so we'll pop those in. We're going to have to squeeze them. So rho sine phi cosine theta for x minus 2 times z, which is rho cosine phi. We did it. And there's our fully set up integral. All right, now we're coming back and doing these the hard way. All right, so our first one, we are setting up our integral using spherical coordinates now. And so, as per usual with spherical, let's look at a theta equals constant slice, and if we imagine a doorway cutting through this thing, the slice that we're going to get looks something like this, right? So vertically it goes up 2 and then out horizontally 3. Now let's think about so setting phi. So pick some random angle, move rho. So we're moving rho, starting rho at 0, and moving it out to this top side is where we want to stop. Rho equals the top. And if we pick a different angle, maybe like that one, start rho at 0, move rho out to the top side. But if our angle is big enough, if phi is big enough, and we're like close to pi over 2, now rho is starting at 0, yes, but we're not stopping on the same side. Right here, we're stopping at rho equals the side of our solid. And so actually we're going to have different start-stop instructions, right? There's some kind of special angle here where after that angle we're getting different instructions. Because of that, we need 2 triple integrals to set this up. All right. And so let's do this. So for our first one is going to be this kind of top, and our second integral will be the other side. So our first integral up here. All right, we're moving rho from 0 up to the top. To be more precise than top, all right, we need an equation for our top side. Our top side is z equals, right, looking over here, the vertical goes up 2, z equals 2. And in terms of spherical coordinates, z is rho cosine of phi. And we want to figure out where to stop rho, so we just need to solve this equation for rho. And so those are our stopping instructions for our first integral for rho. Well, and what phis are we doing this for? Well, the starting phi is phi equals 0, or pointing straight up. And we are stopping phi at whatever angle this green star is, right? But we can be a little bit more specific. Right, at that angle, we have a nice triangle. We have 2 and 3, and so that angle star is going to be inverse tangent of 3/2. We can write that. So this star is inverse tangent of 3/2. That's a fine and, in fact, good exact way to leave that. And what thetas are we doing this for? We're looking at our 3D picture. Looks like theta is going to be from 0 to pi over 2. And so here we're going to have the same function, translation as we had above. So let me not include that and just focus on the heart of this computation, which is figuring out our limits of integration. All right, so to this, we'd have our second integral. The bottom half over here, or I guess side half. For here, we're always starting rho at 0 and ending rho at the side. And so here, we need to get an equation for our side. Our side here is a cylinder, and we can kind of see that here. It says vertical at 3 in the r direction, right? So this side has equation r equals 3, and in spherical, r is rho sine phi. Whenever I write it down, I'm double checking myself with a triangle picture in my head. All right, so solving for rho, we get our stopping instruction. So 3 over sine phi. Now, for what phis are we doing this for? Well, we're starting at the green star angle and then increasing that angle, increasing phi until we get to pi over 2. So starting at inverse tangent of 3/2, right, that's our green star angle, and then moving up to pi over 2. And then what thetas are we doing this for? The same as before, right? 0 to pi over 2 for theta. And again, we'll have the same function translation and dv as we did before when we were using spherical coordinates. All right. Next, we're looking at our portion between these two spheres and doing it the hard way, which for us is going to be with cylindrical coordinates. And so once again, with cylindrical, we're thinking about which variable we want to move first. And here, I think probably cleanest still is moving z first. And so if we pick an x, y, and we move in the z direction, for some of these, we're going to be starting at the inside of the sphere and popping out at the outside sphere. But for other xy's, say near the edge, we're going to be coming in at z equals 0 and popping out at the outside sphere. I think we can get if that's feeling a little bit strange, I think if we get kind of a side view here, we can see this happening a little bit more clearly. Right? So if it's kind of close to here, we're going to be starting on the inside sphere and stopping at the outside sphere. But if we're near to the edge on the right, then as we move z, we're going to be starting z at 0 and stopping at the outside sphere. And so we're going to have a change of instructions. And so once again, we'll need two integrals to set this up. All right, so here we go. We're going to have, let's say, this kind of more inner portion. We'll use integral 1 to do that. And the outside portion, we're going from 0 to the sphere through integral 2. All right, so for integral 1, we're moving z from our inside sphere to our outside sphere. And so I suppose we need equations here. So our outside sphere with radius 2, right, that's x squared plus y squared plus z squared equals 4. And our inside sphere would be x squared plus y squared plus z squared equals 1. And so to start at our inside sphere, we just need to solve our equation for z. And we are in the positive z direction, so right, we'll get the positive square root of 1 minus x squared minus y squared. And we'll be stopping at 4 minus x squared minus y squared. And, well, what's the shadow for our integral 1? That's this inside circle here, right, underneath our inside sphere. So it's going to be a unit disk. And so in polar, we can move through that. Right, that's using thetas from 0 to 2 pi and r from 0 to 1. Right, and we'll have our same cylindrical function translation and r dr d theta and all that. And also, let's take these minus x squared minus y squareds and swap those out in terms of cylindrical. All right, we can write those as minus parentheses, x squared plus y squared. In other words, we got 4 minus r squared and 1 minus r squared here. All right, for our second piece, here we're moving z from 0 up to our outside sphere. And what's the shadow going to be there for that integral? Well, now it's this ring around our unit disk, right, up to radius 2. And so maybe let me draw that again. Right, so here's our shadow, roughly sketched, 1 to 2. And so to move through that in polar, all right, again, we're using thetas from 0 to 2 pi. And for each of those angles, say this angle, that theta, we're starting r at 1 and stopping r at 2. And that's going to be consistent the whole way through. All right, our last problem, I actually have a solution for in another video. I have not made this bit.ly link, but I'm going to guess that 253 Pac-Man is not taken, and we'll see how it goes. Good work today, everyone. I'll see you next time.